which continues on comparisons, as we saw some of yesterday, is Tess, talking about comparisons in North America. So, Tess, are you there? I haven't checked yet.
Yes, I'm here. Give me 1 second. Is that good to you? You can see the right sorts. Perfect.
That's great. Please go ahead.
Great. Well, thanks, everybody. It's nice to be here and it's exciting to have a conference on this topic. I should say, I guess this work was done several years ago, so bear with me if I'm a little bit rusty. But this was my first PhD project. So we started this work in 2017 when I feel like there were many fewer discussions of this sort. So it's cool to see this work sort of informing and being part of a workshop like this. So in particular, this work focused on emissions uncertainty of smoke from fires in North America, sort of within a global context as well. Since we were using a global chemical transport model, we looked across the world, but then focused on North America. For a workshop like this, I don't necessarily need to show this slide, but for this project, we liked to kind of go under the hood and explain to folks how these different fire emissions inventories were put together. I think this has probably been talked about several times over the last couple of days, but just wanted to point out that in this work, we were comparing a couple of bottom-up inventories, in this case, what was available at the time, so GFED 4S and then FIN 1.5. Which, as most of us know, use burned area and then some lab studies for emission factors and some other variables as well to build out the mass of species emitted. And then we compared against a couple of FRP or fire radiative power based inventories, QFED and GFAS. And at the point when we were doing this study, most modeling studies didn't test air quality and radiative uncertainty associated with fire emissions. So we took these four emissions inventories, we did an analysis of just the inventories, and then we put them into GeoSChem, which many of you are probably familiar with, but it's a global chemical transport model that lets us simulate how different chemicals move through the atmosphere. So I'll just step you through some of our emissions analysis. At the time we were doing this, what was available for all four inventories was 2004 to 2016. So across those 13 years, we were looking at total annual emissions, mostly focused on black carbon and organic carbon. But we did a similar analysis for CO and NO, I believe, because we were getting a lot of questions about that. But first, just to start with, we looked at Boreal North America. And to orient you, GFED and FIN, the bottom-up inventories are in those warmer colors, and then the FRP ones are in blues. And we can generally see that the FRP-based inventories are larger for both species, although GFED is pretty close, and then FIN is quite a bit lower. And these are sort of box and whisker plots. And so the large range of those boxes shows that there's significant variability across years. If we next look at the contiguous US, we see that GFED, FIN, and GFAS are fairly close to each other, whereas QFED is substantially larger and more variable as well. And then if we do the same sort of analysis globally, we see that average emissions over large regions, such as the globe, differ significantly between inventories, with QFED, again, being generally larger. So then we were curious in trying to do at least sort of a coarse analysis to understand where these differences were coming from. And so what I'm showing here are total annual dry matter from each of the inventories, so basically taking off that emission factor. And there's lots that you could look at here, but basically I've sort of circled some of the more interesting areas where there's differences. And so, for example, in GFED, if you look at the top left, you see sort of that large agricultural region in the middle of the US and into Canada popping out as much larger, perhaps, than in some of the other inventories. And then I've also circled FIN for both species in the Boreal region, where you see a lot more variability than some of those other inventories are showing. And so what we do then is, I'm just showing for Boreal North America because it's a bit easier to see, but we compare sort of the dry matter differences across inventories, which is about a factor of 4 in terms of magnitude differences to the differences in black carbon for this case, which is a similar factor of difference, suggesting that the differences in these emission inventories are largely driven by the underlying dry matter. We also then wanted to compare how these different inventories drive the model against a suite of observations. I believe in this presentation, I'm just showing a comparison against aircraft measurements, but we also used surface observations and satellite observations of AOD to compare against the model. And so just showing a few of those, on the left, I've pulled out the Boreal component of the ArcTask campaign, which flew in 2008. And the black line, if you're not familiar with these sorts of plots, these are vertical profiles. So you're increasing in altitude as you go up the y-axis, and then larger mass concentrations as you go to the right on the x-axis. But what you can see is that in black is the observed organic aerosol concentrations, and then the same colors we've been using throughout are the different concentrations driven by those different fire emissions inventories. And the no biomass burning run is in gray. And so what you can basically see, again, just focused on the left plot, is that fires are driving these large enhancements in organic aerosol, which is what we would expect in a region and an aircraft campaign that was pretty fire targeted. A few interesting things to point out is that Finn basically shows no fire emissions in this Boreal region, which is consistent with the much smaller emissions that we were seeing in sort of the emissions analysis. And then you can see sort of increasingly large enhancements from QFED and then GFED and then GFAS. And both QFED and GFED are pushing the model sort of within the bounds of uncertainty of the observations, whereas GFAS is larger. And then on the right-hand side, we did the same sort of analysis, but for the DC-3 campaign, which flew in the summer or the spring of 2012, I believe, in the Southeast US. And again, I should have mentioned this, sorry, but we filter for the most acetonitrile influence parts of the campaign to focus on the fire influence. And here I'm showing both black carbon and organic aerosol because they have a bit of a different story in terms of those different inventories in this region. The top is showing black carbon, and we can see that GFED, Fin, and GFAS all push the model into really good alignment with observations, whereas QFED is a factor of 2 or more larger than what observations would suggest. Whereas if we look at organic aerosol, QFED is actually pushing the model closest to observations and the others are low. So sort of the biggest takeaway is at the bottom of the slide that there's significant variability across inventories, with QFED generally, but not always, biased high, and Fin generally, again, but not always, biased low. So a couple of slides just to sort of get to the why does this matter? What does this show us for air quality and radiative impacts? What I'm showing here are 2012 annual mean biomass burning aerosol or fire PM2.5 surface concentrations across a lot of North America. A few things to point out: that there are large differences in this fire PM2.5 surface concentration in the western parts of Canada and the Pacific Northwest, which is consistent with those emissions differences. And then what I've pointed out on the legend here are how basically the warm colors, when we originally did this, when the World Health Organization's air quality guideline was at 10 micrograms per meter cubed, we're seeing that fires are pushing pollution above that annual mean limit just by itself in many areas. And now that the World Health Organization has moved that down to 5, we're actually seeing even larger areas where fires alone are pushing air pollution above that number. But again, we're seeing differences spatially, right? So then depending on where people are, there can be differences in exposure. And we're all on the same page. I assume that EPA still has their numbers set at 12. So you could say the same sorts of things, but there would be less spatial areas above that. And then finally, I believe this is my last slide. We looked at the direct radiative effect of this biomass burning aerosol. So to just sort of orient you, these are the same regions we've been talking about for the different columns. And then the top row is black carbon radiative effect. So that's a warming effect, and then organic aerosol on the bottom. And we can see basically the same sorts of trends coming through, that we're seeing differences depending on inventory used, with fin generally smallest and QFed largest. And then just to sort of contextualize what these numbers mean, because if you don't think about these all day, then perhaps, you know, the differences in numbers don't mean a ton, but the range across inventories for the global number, which is often used in the IPCC, depending on which fire inventory is used, is minus 0.062, which is pretty similar to the effect of people on organic aerosols DRE, suggesting that the uncertainty from fires alone is the same magnitude of our understanding of the human effect on organic aerosol broadly. And so with that, this is my last slide. Our sort of three big takeaways are that the dominant cause of differences between inventories is predominantly dry matter burned over North America. Model simulations with GFED and GFAS are closest observations. And then this was our big takeaway, and it seems like a lot of studies have now moved this way, that air quality and climate studies should consider and assess fire emissions uncertainty. So I believe that's it. Thanks for your attention.
Thank you very much, Tess. Finished in plenty of time, so we have a lot of time for questions now. I don't see any yet. Please feel free to raise your hand if you have a question for Tess. Don't all do it at once. Terry, I see your hand.
Hi, Tess. So I'm wondering, given what you've seen, what your thoughts are on the concept of doing a mosaic where you pick and choose different pieces of the inventory, either regions or pollutants or things like that, for different regions, and compile a composite that may be selected to better perform. Given what you've seen, does an approach like that make sense to you, or is that something that would be difficult to do?
I think it could make sense. I've definitely seen more studies in the last few years try and do basically what we did, like, for example, over Australia. I feel like for a long time we used to joke that probably just averaging all the inventories would get us sort of closer to something. No disrespect to the many inventory developers on here, because there are just pros and cons to a lot of them. So I definitely see the benefit of you know, doing a mosaic approach like you mentioned, but I don't know if we necessarily have enough in the literature to do that adequately for all regions, and enough observations to maybe like fully get us there. Although when I give these talks, I often mention how obviously the sort of advent of satellites and pulling in a lot of that information gets us much closer. But I guess in this work, we also discuss how some of the reliance on satellites for QFED, for example, are likely what's leading to the sort of over bias. So I think that's just to say that's one example of why we have to be sort of careful as we do this. And I imagine it would also be challenging as we get sort of updated inventories, and you'd have to redo some of this analysis to make sure that the newer versions are still performing better in certain regions or for certain time periods or whatever. So it's a great idea. I don't know how it would work in practice necessarily.
Thanks.
Yeah. Are there any other hands up? I don't see it.
I'm seeing some in the chat.
Yes, there's a comment and a question in the chat. So Mayon has a question. Would you like to ask that yourself, Mayon?
I can just
that.
read it. Yeah, it's asking about the vertical distribution of fire emissions in the model, which is always a good question. So the like baseline in GeoSChem is to put most of it, into the boundary layer. We did run a sensitivity run where you put, I'm going to forget the exact proportions, but you put a big chunk of it into the boundary layer and a smaller amount above it, and basically saw that there was no real difference relative to observations when we did that. But there's certainly been some work trying to parameterize sort of a better injection scheme. And I've seen some interesting stuff like using Miser to do that, but I think it's often very like fire specific. It's hard to do that like broadly in the model. So there's definitely work to be done there, but I don't think that's probably what's driving some of these differences generally. There's another question I can just sort of keep reading if that works. Did you look at the differences in coefficients and uncertainties of the pollutant type, the different models? Or did we use our own and be consistent with which each source? I'm not sure I totally understand what you're asking. I'm not sure if either Tim does or Paul, if you want to clarify.
Yeah, Paul, if you can turn your microphone.
Yeah, I may not understand the different models properly, but I think from what I saw in the presentations in the previous 2 days, that each model estimates these different pollutants like black carbon, organic carbon, and they had coefficients related to CO or something else to come up with what the emissions are from the burned area or the radiative firepower.
Like an emissions ratio instead of an emissions coefficient, is that?
Well, ratio, I mean, it's just, am I correct that they have, I thought I saw tables up where they would come up with emissions, for instance, black carbon, organic carbon, and they would be basically using a ratio or a coefficient to CO or something like that. I'm not sure. So
That's
I guess
definitely one way to do this. But yeah, in this study and these inventories, they're using dry matter burns and then applying an emission coefficient that's specific to black carbon or organic carbon or whatever pollutant we're talking about relative to the dry matter burn. So in this case, yeah, they're not going off CO. I think maybe Finn does do that and how it's built out, and you can look at that sort of under the hood. But in this case, yeah, we were just their emission coefficients based on dry matter. Does that help?
So those were the same, use the same coefficients to dry matter for all the models? Or are you using what they used?
We use what they use. And so I assume this has been talked about probably in past days. My apologies, I wasn't on. But yeah, most of them use a Kagi et al. 2011. I believe QFed uses an older version of Andre and Merlet from 2001. So we're just using how the inventories were made themselves, since we want to be as sort of close to how they would be used out of the box. Yeah, thanks, Christine, for clarifying. Finn does use emission factors. I think there's a way when it's put into GeoSChem to potentially look at something relative to CO. But in this case, yeah, we're just using them out of the box, but they do have differences in emission factors. And that's why we were looking at, we basically take that off in the first analysis I was showing and look at just the differences across dry matter to try and hone in and show that that's actually the largest driver of difference across these inventories.
Okay, thanks for that clarification.
Yeah, for sure. There's lots going on. That's why I often show that that slide at the beginning, sort of explaining how the different inventories are built out. But I didn't spend a ton of time on that, so it's a good question. Other questions or clarifications?
I don't see anything in the chat or any hands, so we would have 10 more minutes, but if we don't have any more questions, then I would suggest we simply move on with the next talk. Thanks again, Tess. Oh no, I see a hand from Rebecca, just in time.
Hi, thanks for that great presentation, Tess. Really interesting. I just wanted a little bit of clarification about the dry matter burned. You showed those maps. Were those maps that you got from the inventories, or did you back calculate them somehow? Can you speak a bit more about that?
Yeah, we back calculate them by using the emission factors we know and the like spatial variability that's used for them. So sorry, I'm thinking back many years for how we did that, but yeah, we have basically the spatial mapping of how the different inventories use emission factors, and so we're then able to divide off spatially the emission factors to get to dry matter burn. So that's a calculation we're doing.
Great, thanks. And did you showed North America? Does it look the most different over North America, or is it similarly different globally?
I don't know off the top of my head, but I can get back to you on that.
Great, thanks.
There's one more question here, Chuma.
Hello, can you hear me?
Yes.
Yeah, perfect. Hello, I'm Chema from Japan, Japan Institute for Marine Earth Science and Technology, and a very great talk. Thank you very much. So in one of your slides, you mentioned that you estimate the direct radiative forcing of OC and BC, you remember, and by using different emission inventory. So regarding that of OC, I just want to confirm that did you consider the change of the how to say the secondary oxidation process within the atmosphere? I mean, for example, the contribution from brown carbon, lead absorbing part during your model simulation.
Yeah, I guess a couple points of clarification. So this is direct radiative effect, not forcing, that we're showing. And so that's like not looking at the difference from pre-industrial to today. It's just the actual sort of radiative effect of the different components. And so to your brown carbon question, no, in this study, we don't account for brown carbon, but in follow-on studies that I did in our group and that other folks in our group have done, we did hone in on sort of characterizing brown carbon better. But in this case, yeah, we're just considering organic aerosols as scattering. Yeah.
Right. Thank you so much.
There is another question in the chat there from Jan Eoff on injection heights. Do you see that, Tess?
I do, yeah. So there's a question about for the burned area inventories, if we use monthly average injection height. So this is what I was talking about before. When we were running this study, there wasn't the option in GeoSChem to sort of change or use a different injection height in a more granular way. There is now a way to do that using like the GFAS sort of injection height variable. But so what we just did is it doesn't change over time. It's just mostly into the boundary layer. And then as I was mentioning, we did a sensitivity study where we injected, I think it's about 30% above the boundary layer, and basically show that there's almost no difference in our model observation comparisons when we do this injection height sensitivity. But yeah, there's no temporal difference with that.
Keep coming. Here's another one.
Yeah, I see that. So yeah, I showed vertical profiles when the model is pushed by these different inventories. This is, yeah, I'm just trying to understand this. So this is, all of this information is published in a paper in ACP in 2020. So you can see all of this on the web, but we ran these runs in GeoSChem ourselves. Basically, you just decide your inputs for GeoSChem. I mean, I'm making this sound very simple, but people spend entire PhDs on this. And you just basically switch to a different inventory. You run the model over the specific months or years you're interested in, and then you compare against observations. I guess to clarify, we're able to sample the model in space and time to these aircraft tracks. So it is like a one-to-one comparison. And we can also do that for the the surface observations, we compare against improve, and you can select in space and time to those substations as well. And then we also actually have a way to sample against AOD, basically to pull like satellite tracks from the model, again, in space and time that are relevant. So I hope that answers the question. Carrie, feel free to follow up if that's not clear. Yeah, okay, great.
So it seems that's it for questions on your talk test. So thank you once again. And we